Our next speaker is Miha Ravnik, and I'll shorten his title. It's The Design of Nematic Defects.
Perfect. Okay, so thank you, Randy. Thank you. So I think I'd just like to start by, we are now sort of mid through the workshop, and I'd just like to, thank everybody for this great effort. I might just say I'm really enjoying the great science that we're seeing, and I think so far it's been really great. So I think it's really great. Thank everybody for this effort, for of course traveling here, but actually also for the effort of the great science that you're talking about and that you talked about, are talking about, and also we'll be talking about in the next 2 days. So my talk today will be on some of the bit more recent works that we are doing in the line of defects, and the talk will be mostly on so what I would like to put as a sort of a crossroad between active and passive complex fluids, active and passive nematic liquid crystals, right? And I think it's really by working at this interface between the two, I won't say communities really, but it's because the communities are actually they mix quite well. I think one can draw maybe interesting idea across the field. So the talks which you'll talk about is actually, these are contributions by various collaborators, students, and so on. I think I should mention, so this is the work by many excellent, talented people from Ljubljana, and the experiments which I'll talk about are also from the group of Igor Mušević. He's in the audience, he's speaking tomorrow. Then some of the numerical input was also from the group from Sharif, so a very talented and capable visiting PhD student in Ljubljana, Masumi Hashimi. And then there will be some experiments which come from the group of Ivan Svanik, who's also talking on Friday. So having this opportunity to say, and I know that the audience is very diverse, I'll just say that we work actually on quite different, on several lines in our group, and today I'll just talk on some, right? So we talk, one line which we do is a lot on colloids and structures. So this is a line that's been in the group for quite some time. And I think there's some quite interesting lines which can come out, and I'll talk about this recent two here. But then we also work on the line of photonics, so soft matter photonics, where in particular like the keywords that we're after, right, is like how can one use anisotropy in the context of photonic crystals, metamaterials, So can one smartly control light? Then we also work on the line of what I like to call fluidics of complex fluids, and this is also, so this is essentially macrofluidics of passive liquid crystals, but also active liquid crystals. And there's some recent works, and I'll mention some of this, which is currently yet unpublished. So the last part of the talk is unpublished at the moment. And there's an industrial line which you have on the group, which is we're working on protein aggregation in the context of designing biopharmaceutical drugs. So this is sort of what we do, and so now I really go to the talk, and so I like to start with this cartoon because this is somehow underlines the system that we'll be talking about, and either being an active or a passive liquid crystal, in the sense that the system we'll be looking at is actually it's essentially a combination of two phases, and there's a continuum phase, and this continuum phase will be a nematic. And when I say nematic, I mean it can be a passive or an active nematic, right? The main difference will be that if this is a nematic, then this, I try to draw it as a rod, right? And I call this dimension A, right? Then we're usually in the regime of, say, nanometers, right? This is molecules then. But if this is in the context of now an active nematic, right? You know that this basic ingredients which today people speak in the context of active nematics, for example, the materials by the Brandeis people, and this also spread now around. This is more now in the range of a micrometer, right? And what we're after really is, how does this surrounding fluid talk to the surrounding, either being particles, they can be also channels, right? I wanted to use the word confinement. So how do they talk to one another? And we worked on various lines on this in past years, the colloidal assembly and so on, in particular being in the passive nematic regime, but I think there are some results which are also trying to do some contributions also in the active field. Now, saying that, it's really that this talk will be at this, I want to say, an interface between an active liquid crystal and a passive liquid crystal, and why this can be done, right? So please remember talks, we had yesterday an excellent introduction, so I hope I can rely on that, right? By Julia, by Gareth, by Tom. So there's several people spoke already on these lines, how this passive and passive and active nematic community or fields, right? How they are related, right? And I'll just say that yes, these materials have very analogous material characteristics. Of course, and this is, I think, an advantage which we can use, to go from one side or to the another. Now, a bit of a motivation on defects, right? Why one would like to think about topological defects, and the first maybe is in the context of passive nematics. This is definitely a statement which is already now quite many years old, right? That actually if one does a quench transition, so if you take a nematic, heat it up, right, and then let it cool down rapidly, this thing undergoes a mechanism, a Kibble mechanism, and it's believed that it's exactly this mechanism is behind the formation of our universe in the Big Bang. Right? So this is analogies which are in the literature now for a long time, but and I'll stop here, right? And maybe you notice in the program, right? So tomorrow Igor will talk, I think, much more on these lines. So as another maybe an advantage, right? So passive defects, right? They are very much a part of what I would like to call an advanced material platform. So people, the key works which go here is like people try to think about topology. So various topological aspects, and here I cite just the work by, it's a joint effort between Penn and Boulder. Yeah? And this is maybe this last, this other one which I cite. I mean, there's many, right? So I just have to select some. This is work by from Abbott's group, right? Where they really recently they show, they can really do a self-reporting and self-regulating liquid crystal. So they are really using a transition, right? Essentially, they can you can put your finger on a system, and then the liquid crystal drop will release cargo. In their case, this is just this red dye, but you can imagine this can be a drop, right? Yeah, so it's a very neat and smart application of such a system, where actually these drops they're conditioned by topological defects. Now, from the active line, I think we heard much more of that, right? So far, so this is just a few lines which I'll mention. Definitely, I'll just say that active defects are one of the core elements that today are used to analyze and think on how active nematics behave. So either in terms of how they order, but also I think even more in the context when you go into the regime of what's known as active turbulence, and we heard about this, already here, active turbulence, right? And it's this analysis or being able to control it, and this maybe we cannot control it, to understand it, right? It's really underlying, I think a lot of this field, right? And here I cite this works by the Brightness people, but this is also the work in the epithelia cell systems, which you heard about also yesterday. Now, so the outline, I'll just very, very brief into methods, and then I'll go to the four systems I would like to talk about today. So, and essentially it's fractal nematic colloids and higher order elastic multipoles, and then I'll also go to some notes I hope we could say about the 3D bulk active turbulence, and then actually also active turbulence closed into droplets. Yeah? So the methodology we use is essentially mesoscopic modeling. So it's a continuum modeling. So which is based on an order parameter tensor. And again, I'll just say this is an approach which is well, I think, documented and used in the literature, also validated and explained in the context of experiments. And this is also maybe a point where one can really see now also a comparison or an analogy between how people try to approach and understand passive nematics and how they try to do active nematics. And the main difference they do just is really only in a stress tensor. It's only in a stress tensor, and it's a contribution to Sriram. It's Sriram's idea, right? That makes this difference, essentially in the methodology from thinking about a dense passive nematic and a dense active nematic. Active nematic. So there's really, but it makes a profound difference. Now, methodologically, so we rely on the order parameter tensor, which is essentially a quantity that accounts for the variability of, imagine your molecule, or average motion of a molecule, or an average motion of some active, either be it bacteria or a cell, or in the context of a passive nematic. So how we solve that? So we do this with a hybrid lattice-Boltzmann algorithm. So it's a method which is, again, it's taken from the literature, because grown for many groups. So here I just give a bit of this is really where we spoke about how really exactly implemented this work. And hybrid lattice-Boltzmann, what it does essentially, it solves in a finite difference scheme the dynamics of the liquid crystal, whereas in the lattice-Boltzmann scheme it solved the Navier-Stokes equation. So this is, and they're coupled and they talk to one another. Now, fractal nematic colloids. Now, fractal, right? I'm not sure we heard the word here on fractals, And of course, you know, right, that the key property of a fractal is self-similarity, right? So if you have a fractal pattern, right, so it should be self-similar at different length scales, yeah? So if you go at some scale, or if you zoom in, or if you, in principle, you can zoom out, right, the patterns should be self-similar. And here I give just these two, yeah, just these two, just two examples. This is nature. This is just a plant, right? Maybe you had this for lunch recently, right? But it can show up. So there's this fractal phenomena also in very different systems, like these defrosting patterns on Mars. So essentially, what you see, this is sublimation patterns that come. Here is sublimation patterns of CO2 that were taken by NASA at the surface of Mars. Right? So this is the fractal phenomena. I just want to show you. It really goes. Yeah? It's extremely broad. Right? Yeah? This one maybe central quantity which people use to talk about fractals is the fractal dimension. Yeah? And essentially, this fractal dimension is this number. Yeah? Is this number, right? Where people try to essentially, I won't say it's a power law, right? But yeah, in a sense, yeah, it's a power law. So of course you know that for a regular sphere, right? If you have a sphere, your radius grows as r squared. Yeah, it's an r squared of the sphere. Whereas if this sphere was not a sphere but some sort of a fancy fractal, yeah, this surface area would grow as an r to the power of the fractal dimension. Okay, it's this number. Yeah, that's essentially it tells you a little bit of what kind of fractal do you have. Yeah?
Why did you say d upon 2? Why not only d?
It's from the literature. This is literature. This is standard literature. Yeah, we took this one. That's it. Nothing profound there. But, I mean, from our perspective. Yeah, but it's from the literature. Yeah. People define it in the literature like this. Right? So, and the system we would like to look at is really Koch stars. And so essentially one of these basic geometrical fractals, so this is regular fractals, right? We have this regular self-repeating fractals are Koch stars. So this is attributed to Helge Koch, early 20th century, early 20th century. And the key thing when one thinks about this such a fractal is really one introduces this notion of iteration. Yeah, and what she did, she started with a triangle, and then you can see that just by bisecting this line into another and adding another triangle, this is how one can build a pattern, and this is called the Koch fractal in the literature. But this is something what we will all call maybe like a snowflake. Yeah, this is something called how we visualize how the snowflakes look like, right? And it's really similar, right? So if you go zoom in, zoom out, so this is maybe one of the most standard. I mean, one of the you have to take one. A fractal. And what we will do, so essentially we will take this fractal, we'll take this, make it into an object, this is something what they can do in the lab of IGA, right? And cover it with the right boundary conditions, perpendicular ones, and look what does it do, and really, so if you do that, you can do this numerically. This was finite element scheme, right? Essentially, what you see is, right, so what we show, so this, imagine now you have the surface of a fractal, so different iterations, grow with complexity, right? And you see that now what happens is that, the nematic response and actually is frustrated by this fractal surface, fractal surface. And the more you frustrate it, the more, I would say, it responds in a more complicated way. And so what you see here, so this red tries to show you that this is where nematic is sort of quite well aligned. So essentially this is a plot of your degree of order. And what you see, so this blue points, this is actually the course of topological defect. So if you see a blue point, this is where you have a defect. Right? And you see that by increasing the iteration, by increasing the complexity, I hope you see that this complexity in the defect just starts to grow. And it grows substantially. Right? So if you now count these things, right? So for iteration 1, you have a given number, but then you see this grows substantially. You go from say 10 up to here, you're already above 100. Right? So this goes very quickly.
What's the difference between the two columns?
So here, this is same, except that here we try to show also the molecular alignment. So this is just here you also show molecular alignment, but actually it turns out that what this molecular alignment can do, so it can align on average along the long distance of the particle, but it can also align along the short distance of the particle. So there are two metastable cases in principle. So this is why I show two columns. Now, of course, people will say, well, self-similarity, right? But we're working with a material, right? So there must be some scale, right, where this ends. Where this ends, and of course this scale, this dimension, right, of course, will be essentially the size of our molecules, yeah? Of our molecules. But this can be molecules, but if you think in the context of nematics in terms of the colloidal nematics, yeah, this can be also in the micrometer dimension, yeah? Micrometer dimension. So it really matters if these particles are small or large, yeah? If they are small or large, all right? And this is this ratio between the particle size and, yeah, this nematic correlation, like essentially, yeah, the size of your molecule, of your nematic molecule. You see that your system changes, and I said, right, the blue is the defect, right? So here you will say that essentially all the inner side, yeah, gets frustrated to such an extent that everything melts. Yeah? So essentially you have an opposite effect, right, which we see here to capillary condensation, which is known in from other lines. Yeah? I said Igor's group, they can do that. So it's a smart 3D printing scheme, and you see that they can really make such particles, iteration 1, 2, 3, and so forth, on. And I hope you see the scale bar. So this is 2 microns. So the particles are roughly 10, 15 micrometers across. Yeah? And now when they really put this into a cell, right? Into a cell, you can really see and do a polarization microscopy with this system. So under cross polars and also with the lambda plate, you see such I think beautiful images, right? And if you then you work on what these colors mean, you can work out that these are really there's really an array of defects which forms along the particle surface. Yeah. So doing this analysis carefully, you see that these defects always come in pairs. So it's a pair of a +1 and a -1 half. Which show on the inner and the outer tips of the particle. And if you now really count them, so the number of defect pairs as a function of this fractal iteration, you see it grows. It grows exponentially. And so Massima, she was really good. So she worked out this formula. So there's an analytic formula how it grows. And you see that with iteration 4, you already did 400. So you can just, you really have many. And this maybe other comment to make here, right? I said fractals are about self-similarity. Well, so we're really worried about how self-similar are they, right? So if we zoom in, zoom out, right? Can a nematic be self-similar at multiple scales? And saying that, right? So here we've introduced just very basic, I won't say correlation functions, but just sort of geometric functions to characterize that. And here, essentially going across different iterations. So if you see red, it's self-similar. If you see white, this is where it's not so self-similar when you go across different iterations. And if you try to put this, integrate this, put this into numbers, and trying to answer this in a simple, with one number, right? We can say that the vector is self-similar, at the scale of more than like 95%, better than 90%, whereas the profile of the nematic degree of order is to the order of 60, 70, 80%, right? So it just, I think it's quite substantial. Okay, so this is one way, right? And so I hope I show you the fractals, fractal idea of fractality. One can really design, in this case, a whole arrays and fractal patterns of topological defects. Now this is a recent work with Ivan. It just came out. And here the idea is actually to design, actually to be able to produce what I'll just start calling high-order elastic multipoles. So what are multipoles, right? So everybody knows about magnetic multipoles, right? Or electric multipoles, This is something what you all well know. Well, and elastic multipoles is exactly the same. It's in principle a very analogous, a similar notion used in the terms of the elastic distortion of a nematic field, right? So I'd like to tell you graphically, so this is how the multipoles look like, right? So this, I hope you can see these grayish lines, So this would be called a monopolar distortion, a dipole, quadrupole, 8-pole, 16, 32, 64. Okay, so we go very, very high. Very high. So it's this distortion. I'll just have here reference here because I think this first notion was introduced by Tom, and then other people. And really how to characterize distortions, and not only for that. It's really that these distortion types have profound effect on interaction potentials, and on self-assembly. If you do one step further, of course, trying to to introduce such a general approach, the elastic multipoles are always introduced under basic, quite strong assumptions, but that's what you have to do in order to be able to generalize things, right? And definitely, there's this assumption that the vector field it can be written like that. I think this audience knows that the vector field has to have has to be of size 1, right? So showing you that, it means that this nx and y have to be very small. Yeah? They have to be small. That's it, right? Otherwise you cannot do it. And the other thing which you have to take is that your elasticity, yeah, you take it only under a single elastic constant, and it's of this Frank type. Okay, so that's sort of that's something what you have to take. Yeah? Otherwise, yeah, this is how we can talk about multiples. Actually, being math people here, right? I'm wondering if we can go beyond that. Yeah, don't know. Yeah, don't know the right answer. Right, and if you take these assumptions, then you can introduce essentially this solution. So essentially, then you take this use of free energy, you minimize it, and you look for a solution in the terms of a sum, right? As a sum over multiple elastic, what you call now elastic multipoles. So here you could recognize spherical harmonics. Yeah, this is r. This is the distance from your center of your multipole. This is some scale, and this will be your multipole coefficient. Yeah? Giving you the strength of a given multipole. You just invert the formula and you can really calculate it, right? And that's what we'll be doing. Yeah? Saying that, right? So where does it have a broader relevance, right? So you see here I show you the multipoles, and in addition I think you will all recognize this as orbitals, right? As orbitals, right? And of course you know that atoms, right? That when the atoms and interactions between atoms, right, are characterized by orbitals, and there's actually a direct one-to-one correspondence between a multipole, and an orbital. Yeah? And actually how far our nature goes, right? Our nature, right? The number of atoms that we know that exist today, right? The complexity of this orbital ends somewhere here. Yeah? So if I really want to use like a language to convince some, like a strong language, maybe too strong, right? Is that essentially if you could design multiples of very high order, you could go beyond what is currently realized, what one can realize with atoms that we know. Now, so how do we try? And I would say just we will try to make them. Yeah, we try to make them and also design them. Yeah. And actually this is work by Ivan's group, right? And actually I'll show you that already, I won't say it's simple, but it's not that complex. Particles actually give you a profound parameter space, and phase space where one can realize these multiples, and that's actually this Gort particles. So we see it's essentially particles of two sizes, which they can create, also characterize optically, measure interaction potentials, and so on. So there's experimental part to this, and I'll move to the other side. And I think this key addition to that, right, is not that they can just make some particle and that's it, right? Is that actually they are able to vary multiple parameters of these particles, right? And when I said parameters, what they can do with, and this is smart chemistry, right? Smart chemistry, they can control the size of this upper, I'll say sphere. They can also control how far it goes, and they can also control the anchoring type on this bottom side, which, I mean, in their case, it's a tilted degenerate anchoring, which is quite uncommon, right? For people who know a bit better, this is quite uncommon. So it's quite a smart system, right? And they can do that. It's smart chemistry, right? It's smart chemistry. And what we did, right? We did this numerically, right? So we threw this in the computer, right? It worked quite sometimes. So there's a lot of computer time behind this, right? And we varied all that. Okay, we varied all that, right? And say, okay, how smart are we? Are we any smarter from that, right? And so from this, okay, it's fun and interesting, but the question we were after is really the multiples. And so what we did next is we analyzed the multiples of each of these particles. So this is again exactly this. All these possibilities are now hidden here. So essentially, this axis tells you how far is this upper sphere. This is the radius of this sphere. These numbers tell you different anchorings, and essentially each column gives you a different multiple. So we varied a lot. Okay, we varied a lot, and now seeing that, right? What I'm showing you that is, I hope you can realize, right, that there are regimes, right, that by playing in this parameter, this material space, one can really change the regimes of which of the multipoles will show up. So here definitely you have the dipoles. Here you see that the leading one is the 4-pole, right? If you go here, right, if you're somewhere here, you see you always have a 16-pole. Right? Up here, you see it's a 64-pole. Right? So we really have this richness, this extreme richness in terms of what we can do. So there's this large variability of the multiples, and reminding you all again, right, that this variability directly affects the interaction potentials and the possible self-assembly. Right? We didn't do that, right? But it's there, right? it's there. And now, seeing that, right, making this analysis, right, we wanted to be a bit smart, right? Can we sort of say that's the multipole we want, right? How do we make it, right? And I started with this image, and if you look at it, right, these are my multipoles, right? And if you look at it for substantial enough amount of time, right, you essentially see that the difference between these multipoles is how this director distortion, I'll use the word wiggle, yeah? So how many wiggles does it make when you're somewhere further out? You see here it goes straight, here it goes like this and back, here it goes in, so it makes such wiggles at the end, right? And if you look at this, a bit further on, you realize that you can realize such wiggles already with basic spheres, essentially with chains of spheres, right? I don't want to have all these fancy particles. I try to avoid that, right? Particles, and it's really that already with simple chains of sphere, one can realize exactly this kind of elastic modes. Yeah, and now if you do your homework again, right? You do the analysis, you can now see that we can really design this. In this case, it's just a simple chain, but you have very, I'll use the word pure multipoles. Yeah, you can have a system where you actually design that there's no, I don't know, 8 pole, or no 15, 5, 1, 2 pole. Okay, yeah, so we can do that, right? And yeah, again, moving in the parameter space. So in this case, it's the number of spheres and essentially the anchoring at the surface. Yeah, and at the back of this, right, where are the defects? Yeah, I hope these red regions, I didn't speak much about them, right? They are very much behind how these deformations wiggle. Okay, they're directly responsible or behind that. Right? So it's really essentially designing how these defects are arranged. This will give you this essentially gives you insight into the elastic multipoles. So now let's shift gear, right? So far this was a passive nematic, huh? But now I'll move to an active nematic. Huh? I'll move to an active nematic, and what I'd like to show is now first a few notes on 3D bug turbulence, and I think this is complemented with, there's quite some on this already in the literature, right? So first it was a bit of something what we were a bit interested in, to sort of, as a step there, and I'll just say it, right? So active turbulence, and it was said in this community, right? So it's a low Reynolds number, it's a low Reynolds number regime in various active matter systems, in particular dense active matter systems where one sees such irregular motion of the these active building blocks, say microtubules, or it can be bacteria, which is actually characterized by the emergence of the defects there. And there's works, I just put it like this, there's a large body of work in here. And now, how does this look like? And I'll just say, so the work starts shifting towards 3D, and there are works in the 3D lines. But I think that at the moment, this large body of work is in two-dimensional systems, in particular because that's where experimentally you can access them extremely well. But how does this look like in 3D? And people who do simulations, on these systems, they saw that, right? So this is now essentially how would a 3D active turbulence look like. So you have a box. Essentially, we do it in a periodic box, and this what you see. These red lines. These are topological defects. These are topological defects, and these blue lines, they try to show you this burst. There's flow field all behind them, but we just show where there's the largest flow. Okay, we just take the regions where the flow is really strong, right? And definitely, I think you can all say that this is an irregular dynamics, right? And there's this loop, they make a complex pattern, which is, now how should they talk about it, right? What should they do? How to characterize it? And there are various lines in the literature, and the one we were after a little bit, right? And please also see this paper. This is from Julia's team, right? Essentially, right? So we looked at these patterns, and the main parameters, of course, that you're usually interested in is the activity. And well, the first thing, right? So you see that's sort of how the patterns look for different activities. So this is some increasing activity. And one thing which I'm sure you will all notice is that this density of defect with activity definitely increases, right? Increases, and so here when on each of the sides of this cube, actually we show also the projections of the flow field. So this is the flow field that's here, and there's this general question, which is how to talk about this, right? But what can we learn from such a simulation, right? Are we any smarter from doing that? And this is why I cite also this paper, right? Is to use mode analysis essentially. So essentially what you do, so you take your Q tensor, right, and you take your velocity field, so molecular field and the velocity field, and you do a Fourier analysis of the system. Yeah? So you analyze it. Yeah? You do a model analysis, right? And so here, please see, this is the wave vector, and this is just wave vector recalculated in a proper length scale, right? In the units of the correlation length. Yeah? Okay. So this is it goes the other way. Yeah? Goes the other way, right? And then one can ask, which quantities do I want to look at? Yeah? And so we selected 3. Yeah? So and essentially, one is the kinetic energy density. Yeah? So essentially, it's kinetic energy of your flow field. The other one is an elastic energy density. Yeah, so this is my elastic term. Yeah, L grad Q squared. And then we also looked at the entropy. Yeah, the entropy because this is it's used in the literature. Yeah, so other people use it. Right, so it's there. Actually, saying this immediately, we see that these two give you actually quite a similar. Yeah, they give you a similar input. Right, similar comment. So I think that the one we looked at a little bit more, right, is now the elastic part. And definitely what you see is, so this is increasing activity. Yeah? So this is increasing activity for some value to up there, right? And you see that this peak moves to larger case or to the shorter length scale. Yeah, to the shorter length scale. Yeah? And we can plot. Yeah, one can plot this peak value. Yeah. Also, we tried fitting with some function. We have no. I don't want to claim anything too much on this power laws that we try to fit. Yeah. So when seeing that, right? So can we make a further statement? Yeah. Can we make a further statement? And one thing which we, of course, plotted and which one can do is what quantities can I look at, right? And one which we did was the defect volume fraction, right? And I showed you, right, that the activity, right, the system. So this is different activities, right? The defect volume fraction increases, and if you now plot this defect volume fraction as a function of activity, yeah, I mean, the black lines, the black dots, these are the actual calculations that we did, right? The dashed line, this is a guide to the eye. It's a linear, right? It's a linear, and if I try to put the linear function on that, you see that it doesn't cross at 0, right? Which people will say, yeah, so I shouldn't say it's linear, right? And we tried with some power law function, and that's what it gives. So I don't want to claim too much on this power laws. Okay, one should worry a bit more and do a more careful, do more runs and so on. So the black dots are definitely the results that we got from the full numerics. The rest is very much I don't want too much to emphasis, but. Definitely, so you see, right, that from this defect volume fraction, essentially one could introduce something what we'd like to call a defect length scale, and people have thought and worked in this direction, yeah. So which is essentially an inverse of this density, yeah, inverse of this defect volume fraction, and saying that, right, showing it as defect length density, actually one can compare it. So this is this orange lines. Actually, one can compare it with the values of these peak values that we got from the Fourier analysis. Yeah, I can compare them. Right? How do they look like? Right? What's there? Yeah. So this is two different signals, and I'll just say they compare very nicely. Yeah? They come very closely. This exact comparison depends a bit on essentially how thick do you take these lines to be. Right? This is it's something you have to choose, and this is we choose the half value of the depth in the order, in the degree of order, right? So they overlap to quite a good degree. Yeah, I want to say that they're the same. Yeah, I want to say that, right? So they're quite similar, right? So and essentially, from this analysis, what we're trying to say is that this essentially there is maybe we could use the word length scale, right? I don't want to overuse it, right? So essentially, there's defect. There exists some sort of effective average defect separation in the systems, yeah, which of course shrinks with an increasing activities, and it's definitely seen in the energy spectrum. So thinking in this line, right, this could explain perhaps these changes in the elastic energy density as done in the model analysis. Another thought which we did a little bit, right? We thought a bit about the energy analysis, energy analysis of these systems. And of course, this is an active system, so you have a constant influx of energy, but there's also dissipation. So, and of course, if this is a dynamic steady state, so there has to be a balance between the two. Yeah, so the dissipation. And what we did, right? We thought a little bit how to look at them. And really, if you're people liquid crystal community know this quite well, actually, right? That one can write a dissipation function. And actually, I'm not sure if this is a good word, right? But this is essentially how energy is pumped into the system. Yeah, essentially, and one can just really write it in this form. So I know the experts will probably recognize this. So this is the Q tensor. The Q tensor is the symmetric velocity gradient. Yeah? Velocity gradient. And what we did, we actually calculated this, right? And you said, of course, if theory works, it should work, right? Yeah, it should be there, right? And it really does. I'll just say it like that, right? So we did the integral of this over the whole samples. Yeah? So we did that homework, right? And you see these dots. Yeah, they just quite nicely overlap. Yeah, quite nicely overlap. And again, this dashed line is just it's again I'll say it's a guide to the eye, and which gives you a power law of this theta squared. It's a guide to the eye. I don't want to say anything more on that. Right? So saying this is a bulk. This was a bulk thing, right? So it's an integral over the whole volume. Maybe an interesting question is also about local energy balances, which I think something which would be maybe interesting to think about. Now, droplets, right? So I showed you now the 3D line. I also want to now show you that actually that confinement actually is also in the literature seen as a one way how to tame or how to control the active turbulence. And this, the basic thing which we could cook up, which we could do, was to think about to confine this active turbulence into a droplet, into a droplet. And that's how it looks like. So this is initial condition, so please, ignore that. But now we're sort of getting into a dynamical steady state, and that's this is again my lines. This is my lines. All right, and this is my defect. And what I hope you could notice, right? There's a bit of a difference between the 3D and this one, in the sense that this line is actually a loop. Okay, it's not just a line, but it's a loop. Yeah, and this will have consequence. Again, this is the flow field here, and with this here we use a splay band parameter. This is we commented on the literature. So essentially, it can tell you about the local structure, so the local symmetry of the director profile along these lines. Yeah, and I'll just say here, it changes in time and in space all the time. So there's not only that the loop itself changes, but also the local field around this loop changes.
There's 2 loops.
There's 2 loops. Yeah, there's 2 loops.
But what did it change from?
Nothing. Time.
Time.
It's time. So you will see that from one loop, another loop can be born. Yes, there can be more loops. Exactly. Right? This will be an equivalence to this defect generation, right? Which in 2D people see formation of plus and minus defect. This loop, this is generation of a defect. Now, doing an analysis a bit more carefully, I'll say that, of course, at low activities, right, one expects a non-turbulent regime. And indeed, we see that, right? We see a regime of actually an offset defect, yeah? I'll say, so this droplets which we used had perpendicular boundary conditions, right? So this actually is in the back that we actually got loops. And so at 0 activities, right, in this limit of 0 activity, essentially would get a radial field with a point defect sitting in the center. But when you increase activity, there's a certain regime of activities when the central defect is just pushed out, and then you have a vortex flow, going around into the droplet. But then at some activity, this transitions to this turbulent state, which I just showed you. And again, you can do homework even more. Yeah, Randy, 3 minutes. Yeah, 2 minutes. Yeah, thank you. So you can do this analysis more carefully in the context of these 4 variables. And I'll just say, by varying the activity, we very much see a hysteresis between these 2 regimes. Right? And people will call this a first order transition between the cases, and this is seen in various, so in defect length, defect position, and so saying, right, you saw multiple loops. Indeed, at some activity, the probability for seeing multiple loops increases. In very high activities, in our case, we got to 4 or 5 loops and so on, for a certain amount of time. And it's really in the context of phase diagram, one can really show as the radius and activity. This is, so. The line why I said it's important that that this lines actually change into loops is because if you have a loop, you can think about it in the context of topology. Right? People who do about topology, they know that a long line, a section of a line is hard to talk about its topology except locally, but you have a loop, then you can talk about really, that's sort of a proper defect. It's a proper defect. And if you now, what I show you here, this is actually a timeline. And this is in scale. This is in proper time units. It's in time units. And what we see is that this turbulence, this complex behavior actually can be explained by looking at 4 types of events. So either the loop splits, either the loop annihilates, it merges, or it crosses over. And each of these points, so this blue here, it means that the two loops which were here, they merged. In this case here they split. One of them then annihilated, the other one just survived, and so on. And the fact that we still have one loop is because of the homotropic boundary conditions. So we're able to characterize this. And now, this last point to make. So if we have now, I make this because experimentally, right? People will complain that having this perpendicular conditions at the surface is a bit hard to realize. At least at the moment. That's what I see here. Right? So we change this by putting in-plane conditions. So the general planar conditions, right? The general planar, and this is how the system changes. So in the bulk, you still see this. You see this turbulent behavior. However, some of the loops, you see they opened into lines, and the ends of the lines they started to touch the surface, to touch the surface, right? And it's now that not only you have to worry or study the bulk dynamics, there's also now a surface dynamics of these ends of your topological defect lines. So with this, I conclude, and thank you for your attention.
So one point which I didn't get, so this length scale that you were talking about in the active nematic turbulent phase, do you see, is that the same, like if you look at just the flows, the velocities, do you get that same length scale? Or is that
no, essentially this length scale, that, I mean, maybe a different word would be a defect density. So it's a defect density, and it's in the context of the elastic distortion energy, it's quite very much emergent. So you say at this separation, there's this largest part of the energy.
but
not. So if I show you the spectra, right? So if I show you the spectra, right? So you see here I have a substantial maximum, right, in the elastic distortion, right? Here, okay, you say I have a distort, right? I have a maximum also in the kinetic energy, right? Because this will be your flow, right? This will be sensitive to your flow. So you might say this will correspond, but say when this moves with activity here, there's no sort of an obvious claim that there is a length scale here that I could attribute. So there's the same scale feature in your system at the level of the flow field. So you say that there is definitely some feature, right? So some length scale in your order parameter, in your orientational order, but there's no obvious emergence in the flow field scale.
So, next time, who's speaking?
me, yeah.
Yeah, good. Okay. Yeah, Paula will ask while we're studying, while we're transferring.